இப்போ நம்ம பார்க்கக்கூடிய 7வது பகுதி சார்ஜ் சுத்தி ஃபீல்டுல ஒரு சார்ஜ் நகர்ந்தா ஃபோர்ஸ், சார்ஜ் நகர்ந்தா கரண்ட்னா மேக்னெட்டிக் ஃபீல்டுக்குள்ள ஒரு சார்ஜ் நடந்ததுனாக்கா ஃபோர்ஸ். இப்போ ஒரு கரண்ட் கேரியிங் ஒயர்ல மேக்னெட்டிக் ஃபீல்டு என்ன இருக்கும்னு முதல்ல பார்த்தோம், VIL sin θ பார்த்தோம். இப்போ 2 ஒயர் இருந்தா என்ன ஆகும்னு பார்க்குறோம். இதை டெவலப் பண்ணிட்டு போறோம்.
Okay, I'd like to tell you about the magnetic field due to 2 wires. Okay, so the magnetic field due to 1 wire is, if you use Ampere's law to get it, if this is a long wire here, and it's got a current I through it, and if we want to know the distance away, the magnetic field a distance r away, then we can put an Amperian loop right here, and we can get the current going through that Amperian loop. So the Ampere's law is mu naught times I through the Amperian loop is equal to the closed loop integral, the closed path integral of v dot dl, where those b's are on the Amperian loop and the dl's make up the Amperian loop, and this is the current that goes through the Amperian loop, and that is a dot product. And so just real quickly, the current that's going through this Amperian loop, if I want to know the field, that's the question, is what's the field right there? The current that's going through that Amperian loop is just I. So that's going to be mu naught times I. Now on the other side, do you see if B, let me get my right hand rule going, and so the B is this way, that's B, this is B, that's B, 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 and B. Yeah, those are all B. And these are the DLs. DLs make up the Amperian loop. They're little vectors. And you see how DL is the same direction as B? And so I can, B dot DL is saying take the part of B that's in the direction of DL and multiply it by DL. Well, gosh, all of it is in the direction of DL. So B dot DL just turns into B DL. You get rid of the vectors. And we can say that because B is parallel to DL at all points on the Amperian loop. Then I can pull out the B, because why would B be any stronger here than here, than here, than here? It's the same at every single point on this Amperian loop. And because it's uniform, we can pull it out of the integral. And so that's going to be B. And when I sum up all the DLs, hang on, I can do this because B is uniform at all points on the Amperian loop. And then from that, we can now sum up all the DLs. So mu naught I is equal to, when I sum up all the DLs, it's 2 pi r. Okay, I made that seem harder than it is. It's actually, if you don't have to worry about all those arguments, then you can cut pretty, in no time at all, we can get to B is equal to mu naught I over 2 pi r. Okay, well, we need that for this because what we're going to do is, if we have 2 wires, then we just, we use superposition to figure out, we find the B from one wire and the B from the other wire, and then we just add them vectorially. So let's say we have 2 wires that are both carrying currents, let's say I1 and I2. And let's say they're a distance D apart. And I would like to know what the current is another distance D over here. Excuse me, not the current, the magnetic field. So what's the net magnetic field from both those wires over here? Okay, well, you can use your right-hand rule to, let's just find if this is D also. The magnetic field just from I1 is going to be into the page, and the magnetic field just from I2 is going to be into the page. And so since those are both in the same direction, we can say the magnetic field is just going to be mu naught times I1 all over 2 pi, and the distance that I1 is 2d, plus mu naught I2 times the distance it is just d. And so that is your field strength out there, a distance d. Okay. Well, sometimes they don't always necessarily just add. Let's see what happens if we're in the middle of these. Okay, so current, say, heading down, and this current is heading, say, down also. And these are a distance d from the middle. So well, let's say they're a distance d apart from each other, but this is the middle. This line is the middle. And so this distance is d. And if I wanted to know the field, say, right here, let's call this I1 and I2. Well, the field from I1, if I take my right hand and put my thumb in that direction, it's out of the page. Whereas the field from I2 is into the page. So I'm going to have to call one positive and one negative. I'll call the I1 positive and the I2 negative. So the B, just due to I1, is going to be mu naught times I1 all over 2 pi, and then this would be d over 2. And then I have to say minus, because it's going in the opposite direction, mu naught I2 all over 2 pi times r, but r is d over 2 again. Now it turns out that if I1 and I2 are equal in magnitude, then that's going to if they have the same amount of current, rather, then it's going to cancel out, and there'll be no field right there. Okay. Well, this gets more interesting, though, if they are not in line, but instead we have, say, a coordinate system like this, and we have one current that's coming out of the page, and let's call this a distance A. And here's another current going into the page, and we'll call that a distance A. And we'll call these, we'll say they both have the same current this time. Now if they both have the same current, then let's see, at the origin, the field from the left hand current, this is a wire going in and out of the page, that field is up. Whereas the field from this one is, oh yeah, that's up too. They're both up, and so they would just add. And so it would be mu naught I over 2 pi a plus mu naught I over 2 pi a. You just add them together. But what about if it's right here? A distance, say, b away, up on the y-axis. Okay, well now that's a different story, because the field from here is going to be directed, if I drew a line out to here, a straight line, then the field is going to be going that way, and it's perpendicular to that line. So that's the field. The field from this one, however, is going to be into the page. This one's out of the page. This one's into the page, and it's going to be going this way. And it will be perpendicular to that one. So these have to be perpendicular. These two have to be perpendicular. Okay, well, it turns out that you can do some trigonometry to figure out these angles, but do you see how, because of the symmetry, if these have both the same current and they're the same distance away, do you see how that vector is going to cancel this vector? And we're just going to be left with two of these. So whatever this vector is, it's going to be 2 times that. Now I do know that this magnitude is from this guy is going to be this B right here. We'll call it B1. B1 is going to equal mu naught times I all over 2 pi. And now this distance is a squared plus b squared square rooted. But so is the other one. Okay, and now you have to wrestle with these angles. So you kind of know these angles, and maybe in the next video, I will show you how to do those angles.
இப்போ ரெண்டு வயர்ல என்னென்ன கண்டிஷன்ஸ்ல ஃபீல்ட் ஏற்படுதுன்னு பார்த்தோம். இப்போ ஃபோர்ஸ் ஏற்படுறத பத்தி பார்க்கலாம்.
Okay, I'd like to do the force between two current carrying wires. The two current carrying wires will put a force on each other. But before I do that, I'd like to go back to this problem. So we are trying to find the magnetic field, the distance b up the y-axis. And we had reasoned that the magnetic field due to this guy has to be that way, and the magnetic field due to this guy has to be that way. And that's a right angle. And so I'd like to just complete this problem and show you how you find the total magnetic field from this then. Looks like the total magnetic field, if we look at the x component of this vector, that's going to cancel with this one. So all I have to worry about is this y component, and I have two y components. Okay, so let's call this angle theta. And I'd like you to see that whatever this angle is, see this angle right here? This is, that angle plus theta have to be 90. So I'm going to call this beta. Okay, so beta plus theta is equal to 90 degrees. But come down here and look at this angle right here. I wish I could zoom in again, but this angle right here, to this vertical, to the y-axis, that's a right angle too. And so I can say beta plus, let's call this alpha. Beta plus alpha have to also equal 90 degrees. So do you see how theta has to equal alpha? If beta is 60 degrees, that's going to be 30 degrees, and if that's 60 degrees, that's again have to be 30 degrees. So alpha, this angle right here, is equal to theta. Okay, well, there's a bunch of other ways you can get to that argument, but that's one of them. And so this right here, or I'll use this one. That's going to be b1 times the sine of theta. If that's theta, this is going to be b1 times the sine of theta. Okay, so b1 times the sine of theta is going to be, what I'm going to do is sine of theta is the opposite side over the hypotenuse. But this is also theta right here, apparently. And so that would be opposite A over the hypotenuse. And so b1, if you want to know just the y component of b1, it's going to be equal to b1 times the sine of theta. Now what I'm going to do is, for sine of theta, I'm going to do opposite over hypotenuse. So that's going to be opposite over hypotenuse. Now the hypotenuse of this is a squared plus b squared square rooted. Okay, but the total b then, write it a little bigger, is twice this. So it's going to be 2 times mu naught times I times a all over 2 pi, and then you can put those together. When you put those together, you are going to get, that's going to just give you a squared plus b squared. Okay, so that's the total field that's due to both of those. Okay, I don't know how clear that was, but good luck with that one. Okay, the force between two current carrying wires now. Let me just tell you that when two wires are positioned near one another, and if they have currents in them, they can put a force on each other. So let's have a wire be like this, and another wire be like this. Let's call this I1 and this I2. Okay, now let's just see what force I2 is going to have on it. Okay, the force that I2 is going to have on it is just going to be the force on I2, on wire 2, is going to equal I. Well, let's just see why there's a force first. There's a force because this is creating a field in this region. The field is going to be out of the page. See how I put my thumb down, and it's going to be the hands are going to be coming, the fingers are going to be coming out, and so there's dots here. There's a bunch of dots here. Now they get less as you go out. They're really a lot here, and of course there's X's over here from this. Yeah, there's our dots coming out and X is going in. Now this is interacting with this field by Philb, so it's going to be the force on 2 will be I2 times L cross B. Now this B is from 1, from wire 1. Okay, first of all, can we get rid of the cross product? Well, I would argue that L is this way and B is out of the page. So do you see how if this one is, if the L is that way and B is that way, those are at right angles. So the cross product then just turns into L times B, because you're supposed to take the part of L that's perpendicular to B. Well, all of it is. And then B is going to be the magnetic field due to I1, which is mu naught I1 all over 2 pi r. Let's say these are distance r apart. So 2 pi r. Okay, that is the force on 2. Sometimes they bring the L on the other side. So the force on 2 divided by the length, so now this is a force per length, is equal to mu naught times I1 times I2 all over 2 pi r. Notice that if I double my r, if I double the distance between them, the force actually goes down in half. This is not an inverse square law. Okay, so that's how that works. So the force on it is just going to be mu naught I1 I2 divided by 2 pi r. Alright, I'm just going to do one other thing then. I want you to see that this works for wires, but it also works for charges that are moving by one another. So let's say there's a charge here, Q moving at a speed v, and then here's another charge, Q2 or Q prime, moving in that direction. Let's say they're both positive. Which way will Q prime be pushed? Okay, well, let's see. The magnetic field from this guy is going to be into the page. So this is making X's here. This guy is making X's here and dots here. It's a ring that goes around like this. Okay, this is going to interact with this one's field. So the force on Q prime, should equal Q prime plus V, I'll call this V prime, or times rather, Q prime times V prime, and then cross that into the magnetic field strength, QV cross B, and the magnetic field strength is going to be from this guy. So we're going to get that from this equation, mu naught over 4 pi times Q times V, not prime or prime, these are just Q and V, times the sine of theta all over this distance squared. Okay, now I'd like to convince you of a couple things. This is the magnetic field. Isn't the V perpendicular to the B? See how the V is perpendicular to the B? So I can get rid of that cross product. And then that sine of theta is how is V and R related? It looks like V and R, this is theta. Looks like theta is 90 degrees. And so these both are going to simplify to this. The force on Q prime is going to be equal to Q prime V prime times mu naught all over 4 pi Q times V all over R squared. Okay, same kind of idea as the two wires. All right, thanks. I'll talk to you. Bye.
இப்போ ரெண்டு விஷயம் டிரைவ் பண்ணியிருக்கோம். ஃபோர்ஸ் ஆன் a conductor, force on two wires, force on a charge, force on two charges. இதை வச்சு எப்படி இந்த மூவிங் சார்ஜஸ் டெவலப் பண்றோன்றத தொடர்ந்து பார்க்கலாம்.